I'll talk about, I think, the impact that community codes can have on domain sciences. The specific example will, again, be astrophysics, because I am primarily a computational astrophysicist, and so I think you're probably thinking now, oh, great, another talk about astrophysics from an astrophysicist. I'm just going to go back to writing my code and making it compile again. But I think these lessons actually are applicable across a broad range of domain sciences. The specific examples are drawing from astrophysics because that's what I know. But these things apply to many different areas. And so just to give you a little background on me, I'm a professor at Michigan State University. I've been there about a year now. Prior to that, at some point, I was a postdoc at the University of Chicago working with the Flash Center. So this is also another talk coming from a flasher. So that's a theme, I think. But Flash is a pretty unique code for a lot of different reasons, and we'll talk about the community that's built up around that. But I'll also talk about other community codes in astrophysics. At MSU, I'm primarily a professor of physics and astronomy, but I'm also in our new department of computational math, science, and engineering. And this is a brand new department where we focus on ideas centered around using computation to address scientific problems, both in many different scientific domains as well as engineering, as well as algorithm development and applied math. And so a lot of these issues that I'll talk about are really important to this new department that we've started. And it's a very special, diverse place where we work on these types of problems. And if you've got any question at any point during my talk, feel free to ask. Don't necessarily hold them to the end. You can interrupt me. If we have more of a conversation about these topics, that'd be better than just me lecturing. I actually hate lecturing. Okay, so the impact of community codes, I think, cannot be overestimated. Community codes have had an enormous impact on astrophysics as well as many other different scientific domains. Typically, the problems that we're addressing are highly complex. They're very hard for one person to sit down and write a code top to bottom that addresses an interesting, relevant, pertinent, cutting-edge problem. And so it's much better to leverage the work of previous people or people working together at the same time to address one or different problems with the same piece of code, right? To develop a community around a piece of software that leverages everybody's effort into greater benefit. The benefits of a community code can be many-fold. Right off the bat, they're typically open source codes. And I think open source it sort of mirrors the ideas of open science, right? And in science, we have to have peer review. We have to have openness. We have to have some sharing of the knowledge. We can't just say and put in our journal papers, I solved the problem. I'm not going to tell you how, but trust me, I've got the answer, right? We can't do that in science. And so open source is a critical component of that in our software tools, right? These are the tools that we're using to address these problems, to try to come up with the answer to important scientific problems. And if we keep the source code closed, it's the equivalent of saying, trust me, my answer's right. And I think there's problems with that just philosophically. Open source and community codes have a better chance at being reproducible. Reproducibility is a big issue in science as well. And if your code is out there, if it's a community code, if it's used by a broad number of people who have experience with developing that code and using it, reproducibility becomes a much more realistic possibility. Again, I've already said, no need to reinvent the wheel, right? Why should we keep writing the same solver that does exactly the same thing and gives you exactly the same answer over and over and over and over again? There's just very little point to doing that. So you want to leverage the work that's come before you. And that translates into more science per funder dollar, right? We do not have infinite resources, either in money or time or computing power, right? So we need to leverage things like community codes to get more science done for less investment, both in time and money and CPU time. You know, if you develop some piece of code and make it a community code or incorporate it into a community code, there's a greater chance that that method that you developed will have a bigger impact beyond your individual work, right? Someone else using your code. I think there's very few cooler things than someone else picking up a piece of code that you wrote and doing something with it, doing something different. I think that's really cool, right? It can have tremendous impact and benefit. Ideally, if your code is part of a community, you might end up with better documentation of that code. Now, very few of us sit down and start a software development project and begin by writing the documentation. Maybe none of us. I don't know anybody that does that. In fact, many of us reach the end of a software development project, get the answer that we're looking for, and then go, I don't need to write documentation. it's done what I need to do. But if you make it part of a community project, other people are going to go, what in the heck were you doing here? Why is this line of code there? And so there's some inbuilt mechanism that forces you, that helps you, that guides you, that incentivizes you to actually document better, I think. Still a question mark there. But generally, you end up with better documentation of community codes because you have more people trying to use that code. And so you figure out how to explain how to use that code. And that's documentation. I think there's also a great opportunity for learning from a community that's using a code, right? Different people, we all know different things. We have different skills, different talents, different knowledges that we're bringing to the table. And when you incorporate that into a community centered around one or many pieces of software, you start to trade knowledge. You start to learn from each other, right? You learn new tricks, new tools, new things that improve your work, right? And that's one of the most important things about being part of any community, right? That's the idea of the scientific and academic endeavor. And so when you're centered around a piece of software like that, there's great opportunity for that. Community codes have a long history in astrophysics in particular, and there's a long, long list of what I would dub community codes at various levels, with very small communities, a few users, up to very, very large, very diverse, very disparate communities. There's a website, the Astrophysics Source Code Library, and they have over 800, it might be now over 900 source codes listed of open source codes that are used for astronomy and astrophysics. And these codes range from complex simulation codes, like the things that Dean was talking about and then I'll talk about, to analysis codes, things that are used by observational astronomers even for reducing and analyzing observational data. Some of the big community Astro codes are Flash, which Dean talked a little bit about, MESA, which is a code for stellar evolution, Enzo does cosmology, YT does data analysis and visualization, Gadget is a smooth particle hydro code, Castro is a compressible astrophysics code, Maestro. There's a whole list of these fairly large, fairly complex community codes. Many of these are, I think all of these that I've listed here are open source. They all have communities that are working on different scientific problems and are co-developing these codes together. Community codes have an enormous impact as well. So some of the big community codes that I listed on the previous page, these are the approximate number of publications that have resulted from using those codes. Again, approximate, because it's very hard to give an exact number for a metric like this. But we're in the thousands for some of these codes that are well established and have been around a while. And actually MESA, this module for experiments in stellar astrophysics, is relatively new. The MESA code paper came out in 2011. And so since that time, over 300, maybe close to 400 publications now have resulted from the use of MESA, relatively new community code. And so that impact has just been exponential, quite dramatic. In fact, MESA, I've used it in teaching my graduate level stellar physics class. Right? It's easy enough to use that I got the students to use it and do projects with it in class. So, these community codes can have benefits beyond just doing scientific research. They can be extremely valuable in education as well. So these community codes have greater impact than just lone wolf codes that aren't shared, that aren't developed around a community. So why do we do this? Why have community codes in astrophysics or broader scientific domains in general? Well, in astrophysics especially, monetization is very unlikely. There's not a lot of ways to profit off of the Flash code, for instance, or codes that are capable of simulating explosions in space. The problems are often very complex and difficult for one person to sit down and write a code that does the thing end to end. Flash, for example, has something in the neighborhood of 2.5 million lines of code. Is that about right? No? 1 million. Oh, well. Is it 1 million without the comments? Okay. 1 million actual lines of code, but then a little bit more because of the comments. So that's a lot of coding. I haven't written 1 million lines of code, but maybe not in my entire life. I don't know what the rate is, but that's a lot of lines of code. And I wouldn't want to have to write that from the ground up by myself. And so this communal coding leads to just greater return on your investment of your time and your effort in writing this software. Other benefits include more eyes on the code mean you can find more bugs. All right? Nobody writes bug-free code, right? I hope you all believe that. In fact, the rate is probably, for even a really, really good coder, What I tell my students is the rate is that you write one bug for every 100 lines of code you write, if you're a good coder. 1%. And I'm not talking big bugs, little bugs, right? Up to big bugs. But figure about 1% of the lines of code you write, there's going to be a bug in there somewhere. All right? Be a pessimistic coder. Don't look at a piece of code and go, what could go wrong? Look at a piece of code and go, this is going to go wrong. Where's the mistake, right? So the more eyes you have on a piece of code, the more likely you're going to find that bug or that mistake or that screw up before it has a negative impact on your work, before it slows you down, before you get a wrong answer and don't know it. Right? So I'd rather have people reading my code. The more eyes, the better. Tell me what I'm doing wrong. And typically for community codes, the testing tends to be more rigorous. If you've got other people depending on you, the dean was talking about this as well in terms of doing the regression testing, right? If other people are depending on you within a community environment, you've got to test that code. You make a change, you commit it to the repository, you better test it, right? Because it could screw somebody else up. And you don't want that to happen. And so there's usually, just more typically, tends to be mechanisms built into a community code for doing that kind of testing in a rigorous way. Another reason that we tend to lean a lot on community codes in astrophysics is that the problems we address tend to be very complex, incorporating many, many, many different pieces of physics into one problem. Things like compressible hydrodynamics, magnetic fields, radiation transport, self-gravity, chemistry, nuclear burning, the physics of multi-fluids, complex equations of state, general relativity. The list goes on, right? So these astrophysical problems are typically a big stew of physics that you just put in the pot and stir. And sometimes it tastes good, sometimes it doesn't. So it's really a complicated mess. And so leaning on a community to help you develop that, to build tools of these various different components that are trusted, that are tested, that are reliable, that you can then incorporate into your problem is often critical. Again, it's too complex to sit down and write your own code from the top that does all of these things. So the physics is complex, but then the mathematics is also complex. Of all these different pieces of physics, we usually have different mathematical models that describe them. So you're dealing with, in one simulation application, a mix of hyperbolic and elliptical and parabolic PDEs, some stiff equations, integral differential equations for transport. And so mathematically, it's very complex as well. And so we're often leaning on experienced applied mathematicians to develop algorithms that we can then implement. And so for one person to know all the various pieces of math and physics that's necessary to really accomplish a cutting-edge simulation in astrophysics is a very, very daunting task, right? And I wouldn't expect that, certainly, of my grad students. And so leaning on a community code is critical to be able to really push the boundary of astrophysics forward. So the physics is complex, the math is complex, but then there's also the infrastructure. So this whole training program has been about doing your science at the extreme scale, right? So that's not about the physics, that's not even really so much about the algorithms, that's about how do you take that stuff and put it on 100,000 cores or more, 500,000 cores, all right? So you have extremely high dynamic range in both space and time for most astrophysics problems, right? Dean talked about something that's the size of the Earth and blowing that up and having to understand, in order to get the turbulence, length scales of less than a kilometer or something like that, yeah? So that's an enormous dynamic range, okay? And we deal with that in astrophysics. And being able to do that with a simulation code relies on good infrastructure, good software infrastructure, typically adaptive mesh refinement, which we'll talk a little bit about. Our problems are typically big, and so we have to run them on extreme scale systems like MESA, like Titan, like other machines that are at the cutting edge of leadership computing. Doing that requires really good infrastructure for things like input-output. Just writing a checkpoint file can be complex on these machines. Moving the adaptive mesh refinement grid around is complex on these big machines. Building software on these big machines is hard. Sometimes compilers don't behave the way that you wish they would. Sometimes they're hostile. And you often have many different classes of operators that you're incorporating into one simulation application. And so the infrastructure is just complicated. And one of the things that we often rely on in astrophysics is adaptive mesh refinement. Dean talked about this a little bit, but this is just a cute movie example of what I'm talking about with adaptive mesh refinement. So what we do is we put the resolution of the grid where we need it and not where we don't. And this is how we achieve that enormous range in dynamic scales, is that some parts of the domain are more highly refined at higher resolution than others. Getting this to work right on 100,000 cores is not easy, right? It's not something that I would want to tackle myself all alone. Relying on a community that has developed adaptive mesh refinement, for instance, and tested it, deployed it, and debugged it is critical to doing these types of problems. And then there's I/O. Writing to disk from 100,000 cores or more is a pretty complex thing. I wouldn't know how to do that efficiently. I'm sure if I tried it, it would be bad. It would take a lot more time than it should. And our projects that we're dealing with in astrophysics are typically hundreds of terabytes of total output for a given project, and sometimes hundreds of gigabytes per file that's being written to disk. Right, so this is a complex problem. All right, and you can get some big savings from doing things like machine-specific tuning. But again, that's bringing in knowledge, very, very special knowledge about the particular hardware and software stack that you're working on. And so when you have a community, it's just much easier to have that kind of knowledge within the community. And then you move to a different machine, and then you have to worry about performance portability, which I think Anshu mentioned, right? If you have a community, it's far more likely that you're going to have one person that's an expert on Titan, one person that's an expert on Mira, than one person that's an expert on both, right? So the sharing of knowledge is really important, and that's something that you can get from building a community around a software project and around a code that can really leverage everyone's effort and make these kinds of things achievable, make things like portability achievable from the infrastructure side. Another big part of some of the things we do in astrophysics are particles. So often we're dealing with fluid-based, grid-based codes and fluid calculations, but we also have particles incorporated in there for doing different things like Lagrangian tracers, where we're just literally, it's like a little sailboat on the flow moving around, but then also active particles like dark matter particles, things that are self-gravitating, things that actually cause dynamics on the fluid flow and on the other particles. But you can also use particles for doing things like laser ray tracing through a domain, and also fluid structure interactions in a fluid flow. So this is an infrastructure complexity that is hard to do. Right? And so if you have a community code, something like Flash, for instance, where this has been taken care of for you, you can leverage that benefit and do new things with it, right? If it's already incorporated into the code. So I will mention Flash a little bit. So Flash is a code that has been around for a long time. I think the Flash Center was started somewhere in 1996. Is that right? Yeah. 98? 98. And the first code release was like 2000. So it has a long history of being an open source community code. It has a very big, broad community working on an enormous range of problems, principally in astrophysics, but not strictly. So there's things like Dean talked about type 1a supernovae. I actually work on the better kind of supernovae called core collapse supernovae. And also some problems in stellar evolution. But you've got things that Flash can do that are basic laboratory experiments of certain instabilities like Rayleigh-Taylor and Rickmeyer-Meshkov, nuclear detonation problems, waves on white dwarfs, burning on neutron stars, and also high energy density physics experiments. It is an enormous range of problems that Flash has been applied to because it's a community code it's been around for a while. All of these capabilities and features have been incorporated into the code to treat these different kinds of problems. And so from my perspective, Flash was really a code that did nuclear burning on degenerate stars. It was principally, its target goal. It now does a lot of different problems in astrophysics, but when I picked up the code, it didn't really do all the physics necessary for core collapse supernovae. There's different physics involved from the other kind of supernova. Even though they're both called supernovae, the physics is actually fairly different, as well as the progenitor systems. And so I was able to leverage the work that had already gone on. I didn't need to write a hydro solver. I didn't need to write an AMR solver. I didn't need to write a gravity solver, although I eventually did. I could build off of the work that had already gone on, right? And I could focus on developing the things for core collapse supernovae that the Flash code didn't already have. And so for me, this meant things like a complex equation of state for nuclear matter, neutrino physics and transport, and then focus only on those necessary pieces and then do some science, right? And so going from 0 to publication was a lot faster than it would have been because I was building off of this community code. So just a little background on core collapse supernovae. So this is sort of the pretty butterfly picture kind of thing. So what we're dealing with here is a very different beast than what Dean talked about. this is a massive star that ends its life as an explosion. So these massive stars, they build up iron cores at the end of their nuclear burning lifetimes. Goes no farther than that because iron is an inert nucleus. It doesn't undergo exothermic nuclear reactions. So that core builds up until it reaches some critical mass. It's no longer able at that point to hold itself up against its own gravity, and it collapses. And that iron core, big ball of iron, it's about the size of the moon, and it weighs about 1.5 times the mass of the sun. It collapses to the size of the greater Chicago area, actually maybe a little smaller, in about a fraction of a second, about a quarter of a second. It goes from the size of the moon, size of Chicago, boom, like that. In that space, it goes from central densities of 10 billion times the density of water to in excess of nuclear density. So you end up with something that is essentially a giant solar mass-sized nucleus in space, made almost entirely of neutrons. So like I said, it's the better kind of supernovae. They're way cooler. Those piddly little white dwarfs that blow up. But this is extreme physics, right? This is physics that we can't necessarily access in the laboratory because we're dealing with densities in excess of atomic nuclei, right? And we're dealing with concentrations of neutrons, neutron fractions that are way in excess of anything that we can really access in accelerator beam facilities. In that process, this thing collapses. What stops the collapse? So it's collapsing. This is pretty fast. Size of the moon, size of Chicago in a quarter of a second. It actually gets so dense that the strong nuclear force, which typically holds nuclei together, right? This is the thing that holds nuclei together. At fine enough internucleon spacings, it actually becomes repulsive. And so the strong nuclear force becomes repulsive and stops the collapse almost instantaneously, within a couple of milliseconds. There's a phase transition, is literally physically what's going on. That stops the collapse suddenly, and it sends out this shock wave. And so this is what I'm actually showing here. This purple thing is the newborn neutron star, and the bluish thing is the shock wave that gets launched by that phase transition. And so what I try to study with computational simulations is what drives the explosion. So we know these things blow up all the time. We see it every day. But theoretically, for 50 years, we haven't been able to figure out the why, right? We know it does, but we just don't know why. What's the physical mechanism behind the core collapse supernova explosion? And so these are the types of simulations that we do. One of the big things that's going on here is the neutrinos that are radiating out from the neutron star. So every time you make a neutron in this collapse, you release a neutrino. They actually are able to heat the matter behind this shock, and they drive convection. It's like boiling water on your stove. And this neutrino heating, we think, is what drives the explosion. So think about that for a second, right? How many of you know what neutrinos are? Right? If you don't, it's okay. I didn't at some point. Neutrinos are these tiny, almost massless particles, right? And they don't really like to interact with normal matter. In fact, right now, we have billions of them streaming through us every second. Billions, right? From the sun. They just don't interact with normal matter. The cross-section for interaction is itty-bitty, tiny, right? The densities in this problem are so extreme that the neutrinos are literally trapped. The medium is optically thick to neutrinos because the densities are so high. And so they diffuse out of that neutron star, and they can interact with the matter, and they can heat the matter. And so we think that some fraction of this radiated neutrino energy is what drives the explosion. The neutrinos have got more than 100 times enough energy to drive these explosions. But doing this is an extremely computationally complex and expensive problem. Okay, so it involves that integral differential equation of radiation transport, as well as complex physics of neutrinos, things like Fermi blocking, the fact that they're not actually bosons like photons matters, and all kinds of different fun things. So these simulations can be massively expensive in 3D. In fact, it's only recently that we've even been able, technically, to do core collapse supernova simulations in 3D. And these simulations can cost upwards of 100 million core hours for one simulation, right? And at resolution that's probably not high enough. And so we need extreme scale computing, all right? So this is actually a scaling plot from my core collapse supernova application on Mira. And it's weak scaling. And that last plot is 500,000 cores, right? So we need this kind of scale because 100 million core hours, if you can only run it on 1,000 cores, is going to take a long time. So we need to be able to scale to extreme scales in order to achieve these 3D simulations. And they're just fantastically expensive. And it goes back to planning your simulations, like Dean said. So everything that Dean said, I could just repeat because it was just spot on. When you're dealing with scales this big, you're dealing with calculations this complex, you're dealing with things that are this expensive, if something goes wrong in the middle of that simulation, I throw things. It's infuriating. And so planning is extremely critical. And having good practices, at this scale is also very critical. But this plot, I think, is a pretty good weak scaling study. It would not have been possible without the community code that is Flash, right? Without the community that went into developing that code, without the actual excellent software engineering that went into that code, without this special knowledge that was required from experts that knew the hardware that we were running on to tune the code in order to get the kind of achievement in parallel that this code has been able to do, right? And if I wasn't able to get this kind of scaling, I wouldn't be able to run the simulations that I'm currently running, right? And I didn't do that on my own, right? I relied on the community that was built into Flash, that is built around Flash, that has grown up as part of this code, right? And so I'm benefiting tremendously from the fact that Flash is a well-developed, well-designed community code that is targeted to do many different types of science. But Flash is special. It's been well-funded and professionally developed for like 20 years, right? It was one of the earliest open source community astrophysics codes to do this type of calculation. And there's a core group of developers that have been located at a central location working on the development and design of this code for a long time. This is rare, in astrophysics at least. Most astrophysics codes are done on the cheap, right? You have an astrophysical problem that you're interested in, a scientific question you want to address, and then you tell a postdoc to go write the code to do it, right? Or something like that, right? The code development is ancillary to the scientific problems that are being addressed. And this works from the top down, right? This is usually our funding model, right? We get funded to address a scientific question. If that question requires code development, well, we just have to do it, right? And so that's the way most astrophysics codes grow up and are developed. And so there's less design that goes into them. There's less community effort from the beginning. For instance, I'll talk about a few other codes in astrophysics now. One that actually has very, very similar capabilities to Flash is a code called Enzo, which principally does cosmology. Enzo has adaptive mesh refinement, in-body particle dynamics, gas dynamics and MHD, chemistry, radiative cooling, and subgrid feedback mechanisms for things like star formation and active galactic nuclei. But this code was developed essentially by a community working on scientific problems rather than working for the sake of designing a code, right? No professional sort of software engineers involved. This was built by grad students and postdocs who had scientific questions that they wanted to address. And it actually has a really, really well-established community now. There's something like 12 core developers. They're in very different locations. They rely heavily on online collaboration tools, things like distributed version control and other mechanisms like that to achieve this development, right? Sort of a very distributed model of development, which is very different from Flash, which was very centralized, but to great success, right? So Enzo is a very successful code. Hundreds of publications resulted from this code in cosmology. Big impact on cosmology and structure formation and galaxy formation. Another community code that really grew up from a community in a distributed fashion is something called the Einstein Toolkit, which wins the award for coolest logo of any of these community codes. The Einstein Toolkit is one of the older community codes, and it's was started to do general relativistic simulations. They have an annual workshop. They have rules for merging and contributing to the code. And they even have laid out governance and official maintainers of this code base. So they have taken great pains to really build a community around this code to keep it alive, to keep it maintained, to keep it continually pushing forward to address new problems, to address the same problems in better ways. So that's the Einstein Toolkit. YT. I mentioned this before. This is a code that's principally for visualization and analysis. It started as an outgrowth sort of Enzo, really, of analyzing Enzo data. Right? They wanted a better way to slice and dice the Enzo data. But it's grown to address data sets from many different codes. It's written primarily in Python with some C. But it's become just an amazing tool for a broad range of astrophysics community, and it's even branching out beyond astrophysics. But this is a community code that is not strictly about simulation. This is a community code that is for analyzing and studying and plotting stuff from simulation data, right? So that's a critical part of the simulation pipeline. The Dean mentioned this, right? You've got to have a way to actually look into your data, understand what's going on, get some scientific answer out of these core hours that you're burning. And YT grew out of that need, right? As many of us have experienced, there's often very poor tools for this side of the simulation pipeline, of doing the visualization, of doing the data analysis, of getting numbers from these huge blocks of data. And so YT grew out of that necessity. And it's really impressive what they do in terms of their community development model. And they're now a NUM-focused project. And so this is now centered, I think, in the University of Illinois with Matt Turk. And really great stuff. And they're very active, very friendly community of developers, very helpful, very active mailing list. Okay, but not all areas of astrophysics have traditionally had open source methodologies and community coding approaches. And I think two areas that I'll call out in particular are stellar evolution and radiation transport, broadly defined. There's many examples of codes in these two areas, but they tend to be closed source codes. And that can lead to problems. And one thing in particular that is close to my heart is massive stellar evolution. So for a long time, so I talked a little bit about my type of calculation, the core collapse supernovae. For our initial conditions, we rely on stellar evolution calculations. We've got to have a massive star at the end of its life. That is a completely separate type of calculation, right? And there be dragons. And it's very complex. And for a long time, there was essentially one code and one group that was doing this kind of calculation that we need for initial conditions. And they do a good job. They're very good at it, but that code was closed source. It was very hard to know exactly what that code was doing and why the results maybe changed, why the results were the way they were. There is very little verification against other codes, to say nothing of validation. Validation is extremely hard in this context. And so, you know, like I said before, philosophically that leads to problems if you're thinking about science as an open endeavor. Recently, this new code MESA, which I've mentioned already, is now able to do stellar evolution for these massive stars. And this opens up a broad range of possibilities and really, I think, a lot of opportunity to improve this area of astrophysics. And already, you know, we are able to compare the results from MESA to the old code, verify in some way, get a better handle on why things change when they change. So MESA stands for Modules for Experiments in Stellar Astrophysics, and this is up on SourceForge, actually. Turns out SourceForge still exists. Who knew? And it started with one principal developer, Bill Paxton, who actually retired from Adobe, and he holds like patents to PostScript, so he can pretty much do whatever he wants. And he decided to take a stellar evolution class at UC Santa Barbara, and then decided to write a stellar evolution code. And that became MESA. And he was just auditing this class as a retiree and developed what is now a pretty major community code in astrophysics. And now a group of developers has built up around this, and there's a real community. And there's mechanisms for contributing and maintaining this code. But it started as just a fun diversionary project for him. But he's obviously a very good software engineer. And so this is an example of an astrophysics code which has some software engineering built into it, which is a very good thing. All right. And so this new code, being open source, being a community code, you can do new things with it. And this is something that I did, combining two different community codes, Flash and MESA, to address a new problem that hadn't been addressed before. And in this case, it was going back to those initial conditions that we have for our supernova calculations. Historically, we'd always assumed 1D spherically symmetric initial conditions because that's what comes out of codes like MESA. These stellar evolution codes do everything in 1D. It's just the only way to be done. But we know that stars are actually not spherically symmetric, turns out, just like cows. And so at the end of their lives, they're actually extremely violent in their cores. This burning that builds up this iron core to the critical mass before it collapses is extremely energetic, and it drives very strong convection. Again, boiling water on the stove, right? But we'd always ignored that in my type of calculation because we thought that it probably didn't matter, right? Who cares that the stars are messy, right? Well, this is what a star actually looks like right before it collapses, right? These are convective velocities of upwards of 300, 400 kilometers per second. Turns out that is actually significant and has an impact on the supernova mechanism, and we had just been ignoring that before. We didn't know because we had never done this experiment of asking the question, what impact does it really have? And we were only able to do this because we combined these two open source codes, these two community codes. And this is a movie from that. But it's just an octant, so if it looks weird, that's why. But this is the convective velocity in the minutes before the iron core actually collapses. And so we started from a MESA calculation. We put it into our code flash, and we followed the nuclear burning for the last few minutes until the thing collapsed. And again, if it weren't for the development of these two community codes and then their combination, we never would have been able to address this problem and point out that it actually matters for my type of calculation. And maybe when we're spending 100 million core hours on the neutrino radiation transport problem, we ought to think about our initial conditions and do a good job with that too. So community codes have an enormous impact. And it's not just in simulation. So there's actually a community code for a Python library for astronomy, actual taking astronomical data and reducing it and analyzing it. And this is called AstroPy, written in Python. But there's a fairly substantial community of developers and contributors. And now, the astronomical community is really borrowing ideas of software development, I think from, that really started out in code-based projects and simulation-based projects, and applying it to the way that they analyze their data. And I think this is a very positive thing. And I think this tool has developed very rapidly into a real go-to tool for observational astronomy. And so these ideas of community-based codes and good software practices and design and good practices all the way around extends beyond just doing extreme scale simulation. Obviously, this workshop, this training program is about extreme scale simulation, but these ideas also play a role in observational astronomy and other experimental domain sciences as well. And, well, things like LSST, which is the Large Synoptic Survey Telescope, they're going to be doing extreme scale data science, really. And so these ideas are going to come into play in observational experimental science as well, not just theoretical and simulation science. I would just point that out. OK, so community-based codes are great. Open source is great. What's the downside? There are pitfalls, one of which is if you make something easy to use, people will use it. And you think, well, that doesn't sound bad, until you get to know people. That can be a challenge, right? And I'm not going to pick on Gadget in particular, but I'm just going to use it as an example. Gadget is an amazing code. If you go back to the citations that I listed, it has one of the highest citation counts and publication records of any code in astrophysics. Has had an enormous impact on cosmology and structure formation. It is largely a in-body and smooth particle hydrodynamics code. And you can do things like create the universe using this code. And many people have done so. The development of this was very centralized by Volker Springel, but he made the code open source. And many people took it and used it. It was easy to use. It was stable in that it tended to just keep running. It didn't crash, even maybe sometimes when it should have. But the algorithm was very stable, and so it just didn't crash, made it very easy to use. It was open source. So it has had an enormous impact. But there was a problem with the original implementation of the smooth particle hydrodynamics. And it was basically getting the wrong answer. It should have looked like this, and it looked like this. And it was a problem with the artificial viscosity. And this was identified in 2007. And it was a very easy fix. It was literally like 2 lines of code. You just add 2 lines of code, you're fixed, you're fine. But because of the distribution model of Gadget, this fix was very, very slowly adopted. And many, many people who had downloaded Gadget to do their science didn't incorporate this fix because there was no good mechanism for the proliferation of that fix to these different versions, right? There was no sort of distributed version control. This was just download a tarball and go. Gadget also, the public version that was released, didn't include many pieces of key physics that was actually necessary to do the kinds of science problems that people wanted to do, so they built their own, right? They took Gadget and they built onto it. And so once they've done that, it becomes pretty hard to incorporate new fixes or merge back with some other public version of the code. And so it balkanized, right? People had their version of Gadget. And then in publications, it became very unclear what version of Gadget anyone was using. They say, we use Gadget, and they cite the same paper. But then you go, but no, what version of Gadget, right? And do you have this fix, or do you have this, or do you have this? How did you do the cooling? How did you do the subgrid physics? And so while the impact was enormous, the way that it was distributed and maintained and developed created problems, created code divergence. And this can be a problem in all development models, not just one where you're downloading a tarball and going. You can have this sort of code divergence in all sort of development models. But when you're using something like a distributed version control system and everything is open and the development is in the open, I think it's less likely that you would get something like this. Or at least it's easier to mitigate if you do. So that can be a pitfall of community codes and community projects and open source. Other things include assigning credit. How do you give the proper attribution to the people who have done the work and put in the effort and the time? You know, these codes are really instruments. We use them like a laboratory to address scientific problems. And the builders of those instruments deserve credit. And it's very hard in our traditional academic model to assign that credit. We're taking steps to try to address that. I think there are places now where code development efforts are given much more recognition and given more close to their proper due. But it's still, in the traditional light of the academic endeavor, something that is not easily recognized. And I think that presents problems as well, because there's a disincentive to do a really good job at it, right? Because a lack of incentive to do the job well for most academics. Where do we go from here? So hardware complexity is only increasing, right? Mira is a lovely, basically homogeneous machine, but that's going out the window. You know, we're going to have to deal with heterogeneous architectures and different memory structures and different types and classes of memory, NUMA, all kinds of things like that. It's only going to increase in complexity to get that increase in performance. And so the codes that we're working with today that are community codes that are broadly used, they might be on borrowed time. They're going to need to be retooled, really, and maybe in some cases rewritten to work on the next scale of leadership class computing facilities. Moving towards that, we're going to have to rely very heavily on community efforts, right? Because this is something that no individual can address on their own, right? We really need to rely on the best practices of community code development to be able to leverage everyone's effort in tackling these very serious technical challenges that our codes are going to be faced with on these new hardware architectures, because we still want to do our science. At the end of the day, the most important thing, for at least people like me, is addressing scientific problems. And some of these hardware technicalities are too complex for me. And so I really am hopeful that as a community, we're going to be able to work on these problems together to get to that next level of computing. Things like abstraction of tasks is going to be critical. We're also going to need to incorporate professional architecture and design, things that I'm not an expert at. I'm an expert at the physics, but not at the software engineering. And in order to do science like what I want to do at the next level, we're going to need professional help. And so relying on a community-based code is really the only way forward for something like that. But the funding for that has not gone up. It's really probably decreased recently, and so that's a challenge. And I'd say that hopefully that will be turned around, and I think there's hope for that. But there's no way we're going to get to the exascale or maybe even the 100 petaflop scale without funding for dedicated development of codes. And this is not just the case in astrophysics. This is a case across all domains. And the idea of our community code development is probably going to have to be broadened. That definition is going to have to be broadened, where we're working as a community on individual infrastructural components that can be shared across different domains and different communities that then develop the physics or the science parts that go into these different codes. So I think a community-based approach for the design and deployment of software, both at the infrastructure level, at the sort of software stack level, and then at the physics level and simulation level, is going to be critical. And now I'm just going to plug MSU. So like I said, we started a new department at MSU of computational math science and engineering, where one of the things that we do value is software development. This is something that will be considered in people's tenure package, for instance, that this is something that we consider worthwhile. This is an effort in MSU to really stay at the cutting edge of this emerging area of computational science, right? We've had the president say that there's almost no area of science that isn't touched by computation in the 21st century. There's almost no area of our lives that is not touched by computation in the 21st century. And so we started this department to address that. It's an extremely diverse department, sort of three broad areas of applied analysis and numerical methods, applied mathematics, the computer science, and the disciplinary modeling, things like the actual simulation that goes on. So we're making an effort in this. There's lots of computational physics going on at MSU as well. So I know a lot of you are interested in these things, and so I just put this up here because I know this is a great place to recruit really talented people, and I'm shameless about that. So if you're thinking about graduate school or a place to go and have a great postdoc, think about MSU. Okay, that's all I got. I'm a little early, but hopefully you guys have questions. Thank you.
Questions?
Hi. So when you mentioned about Gadget, what happened to the publications which used previous buggy version of Gadget? Were they retracted? Or?
No. I think even very few of them issued errata. So, everybody just kind of goes, what bug? I mean, that's not, I'm exaggerating a little bit, but no, they were not retracted. Some of them, some of the same authors went back and more or less did the same problem with a fixed version and compared, but that was not universally true at all. Many of those publications are just there without any, erratum saying that, hey, this might not be quite right. They just sit there. Yeah.
Okay, I'm not sure this is a question for you, but can you comment a little bit about the birth of a piece of community code? Mm-hmm. That piece of code, how do I decide that, is it worthwhile to, if I have a few collaborators that are not simply my group, is that enough to start a community code, and what's the process?
Yeah. I don't know if I'm the right person to answer this because I put everything up on a public Git repository. If it's, something that I've used once as a little Python tool to do some piece of analysis or extract some piece of data, I put it up on a Git repo, and I make it public, and I put a license on it, right? Because maybe someone else is going to use that, or maybe one of my students is going to use that. So I think the barrier, I think that maybe in some sense your question goes to the barrier of entry to become a community code, to put something out there. For me, it's very low, right? I want to make as much open and public as possible. Now, sometimes those codes get used. Sometimes nobody but me ever looks at them, right? For something like Flash, going way back, Flash was the combination of really three different major pieces of software and code. And so you have that different model where different disparate groups come together and create one larger piece of code that then becomes a community around it. And so in some sense, that already had a community built in to go forward with that. I mean, for me, the entry is very low. That barrier is very low to create an open source piece of code. And for me personally, if I think about a code being open from the start, I tend to be a little bit better with the way I write the code and the way I document the code, so it's just totally a mental hack that I do to myself to make my code hopefully better. Does that answer your question? A little bit, no? Follow up.
It seems like you've talked about many of the community codes, and it seems like you've seen them start from almost one person to now being used by a few hundred people. So I'm just curious, and how does that happen? Because,
Yeah, so for instance, a code like Enzo, that was largely written in the beginning by one person, Greg Bryan. It was, I think, his PhD project. And so that started there out of the necessity, one, to graduate, and two, to address a scientific problem. But then his group continued to use that code. It became their code within his particular research group. And then just over time, those people go to the different places, they get new jobs, they build their own research groups. And so that was the sort of viral growth of a code, starting from essentially one person with one problem in mind, growing organically to a community and to something much larger. And now it's taken on a little bit more, I would think, life of its own, where they're attracting people from outside of their particular network, right, of their research group and that viral network that grew from that. So that's another example. Gadget grew very quickly because it was easy to use. It was made publicly available at a time when there was very few other codes that could do what Gadget did. And so people took it because they were very interested in questions of cosmology and structure formation, very hot topic. And so Gadget was able to do it and was freely available when there was very few other options for doing something like that. And so that grew very quickly because of that. There was not a lot of effort put into, I think, developing a community around Gadget. It was just extremely timely and extremely useful and did the job, and many people had that need. And so that community grew out of that need and the availability of that particular code. In other cases, there's very explicit effort put into developing a community, I think, like YT, for example. They really have, from the very beginning, put effort into creating a broad community that was not strictly within their own little nucleated research group, right? And so that's, I think, probably a different approach from what other people do. And I think that's growing out of our more modern sentiments about code development and community involvement in open source. And so they took that on and they made it part of YT from the beginning, that we want to have a community. We want this to be community driven. We want this to be community developed. We want people to feel like they have ownership over this code in some way, that they are a contributor, that this is their code, and they have bought into it in that way. And so I think that's another approach. You know, build the community almost first, right? Or at least simultaneous with the code. Not everybody, certainly in astrophysics, does it that way. Most people start with a problem, they start with a code, and then they think, oh, maybe this is useful for other people. Better answer?
Yeah.
At least longer.
Can I follow up?
Sorry, I'm not trying to move over.
Just related, well, maybe on a different topic, but do you see redundancy in these community codes, and is that ever a problem that there are different pockets of community developing codes that do similar things over time?
There's a fair amount of redundancy, I would say. And I'll fall back to the example between Flash and Enzo. They do a lot of the same thing. At least from 30,000 feet, if you're looking at them, you're going, those are the same code. They're not, especially when you get into the details. But there is some redundancy there. And I think that hasn't been a problem up to this point, because it's nice to have a code that can do something similar so that you can verify. You can say, are you getting the same answer, right? Are we doing what we think we're doing, right? So verification is the idea of, am I getting the answer that I'm asking for, right? Validation is, am I getting the right answer? That's very hard to do in astrophysics. Validation is extremely hard. But verification, at least, is the computer giving me back the answer to the equation that I think I'm asking it to answer, right? I'm asking it to solve. And if you don't have another code that does nominally the same thing, but from a completely different code base, that becomes very hard, or at least harder. So I think having some redundancy is a good thing. Going forward, as software development gets extremely challenging for complex emerging architectures, I think we're going to necessarily have to focus our development efforts, especially at the infrastructural level, on less redundancy and more shared code, at least at the infrastructure level. And we're going to have to face the problems of verification and be very careful about that development because of that.
You sort of see the same thing in other communities, right? Like perhaps molecular dynamics, right? You see half a dozen codes that have similar capabilities. And I agree emphatically with Sean, the biggest benefit, right, is that you're able to do things like cross-code comparisons. There are sometimes challenges though, right? And it has to do with understanding the limitations of the particular the particular code, right, that you choose to invest in. Perhaps you're completely invested in code X, right? And I just won't name codes because that gets you into trouble sometimes, unless you're having, a deep down conversation about it. You're invested in code X, but maybe code X doesn't scale quite as well as code Y, right? And sometimes they're doing the exact same physics, but slightly different implementations. Or maybe code X has a little bit better or more physics or whatever, right? Use your qualifier that you prefer, and it doesn't scale as well, or it's not as portable. And there's a lot of different axes on these comparisons. And so that's one of the other components where there's often a lot of benefit within the community of having this, but you also have to understand that there are differences between the codes, right? And so we run into a lot of people going, well, this is the third biggest code, doing molecular dynamics out there, right? Why doesn't it scale perfectly? I can point to it and explain why, right? But there are caveats to accepting that. And so that is one of the challenges, because you have those codes maybe that don't scale as well. Maybe it's because they've taken on the niche of having a much broader breadth of physics and capabilities in them, or whatever, right? But they've developed the different niches.
Yeah.
So I also want to argue actually that there is no such thing as true redundancy, because nobody has the right answers to a way a particular equation needs to be solved. And everyone makes approximations of different types. And so you get sometimes you can get qualitatively different answers based upon what you have done in terms of approximations. And if you don't have multiple independent codes that are doing their own development, you have no way of doing comparison to figure out which of the approximations is a more valid one.
I agree. Even in the example I gave of Enzo and Flash, I said, from 30,000 feet, they look like the same code. But they approach the problem in actually a fundamentally different way, particularly the AMR. They're doing adaptive mesh refinement, but they're doing it in a fundamentally different way. And this can lead to different answers for a number of reasons, right? And so they aren't truly redundant. And having physics is physics, right? And so if we plug in the equations we think we're plugging in, we ought to get the same answer. And so having that is extremely valuable. But doing code-to-code verification is extremely hard, right? Because there's all these small differences, right? You think you're doing the same thing. Maybe you even think you've coded up the same algorithm in the same way. It's hard to know for sure.
So you explained why open source or community codes is very useful, but then have you ever encountered a situation where somebody has a code that you see that can be very useful to the community, but they have some reservations again you showed why you can't, what are some of the pitfalls for making it open source, and how did you manage to convince them, or is it just a thankless job? Or?
Yeah. There are lots of examples of codes that are well-known codes, well-used codes in certain communities that are closed source. That could be tremendously useful codes if they were made open source. I'll speak specifically to my field, which is core collapse supernovae. This is a field that has, until very recently, been wholesale dominated by closed source codes. And those major groups in this field are still holding on to their closed source codes and have no intention of making them open source. And so this has been traditionally a very large barrier to entry for people that aren't coming from those particular groups. And I didn't come from those particular groups. And so I didn't have access to these codes. And so I started not from scratch, I started with Flash. But in terms of the physics that's necessary to address this problem, I did start from scratch and had to come up with my own code and write my own code for those types of things. If I hadn't been starting from a community code like Flash, I'd have been hosed, right? And so that's an enormous barrier in my field, because those two groups that have their code, they lead the field. Everybody is trying to compare to them, and they're supposed to be the standard bearers in terms of fidelity of the physics and the science. But I don't know what their code's actually doing. I have my code, I get an answer, I think it's the right answer, I think I've plugged in the right things, but I get a different result sometimes. And that becomes very hard to know, where's the problem, because I can't see their code. And we're working on doing real code-to-code verification now. But that's a big barrier when the source is closed. And so the other side of that is that I put in a lot of effort to developing my code so that I could have sort of feature and physics parity with these other codes. And if their code was open source, that might have been easier. I might have spent less time doing that. Or because I'm pedantic, I might have done it anyways. But I just like writing code.
One other thing that truly is a big motivator is your funding source comes back to you and says you're going to make it open source. Now that's problematic, and this is part of something we'll talk about after lunch, which is you are a PI, and you've just been told you will do this or lose your funding, and you can do it really badly. Yeah. You really can. You can put your code up in an unfortunate way, and actually Sean alluded to that. That often is a big motivator for people who are really disinclined to do it. They're occasionally compelled. This is not an easy one because you don't necessarily control.
I can write code and make it open source, and you'd never be able to read it and use it.
No, I mean, even within Flash, there is an example of a code piece that was built under the assumption that it would be made public because that's how the funding resource wanted it, but the PI never agreed to release it, and it still hasn't been released. But the point is that even there, having a community code helps because the model that got developed in Flash, for example, from external contributors was that we would negotiate a time during which they could keep the code private and therefore would have their intellectual property protection. And what they perceive, in my opinion, wrongly, but they perceive it as competitive advantage for being able to do their own work and publish it. But then up front, there was a negotiated time at which the code would be made public. And so if they wanted to make use of the infrastructure and have a shortcut to their own getting results, there was a way for their code to become available to the rest of the community also. It's much harder to persuade people when they're doing completely their own development to have that, to make that kind of negotiation. So.
Actually, the last follow-up I'll have on this, I'm not saying this is the last follow-up anybody else can have on this, is that the competitive advantage is a huge barrier, right? And it's very hard to make that scientific argument to get somebody who says, like, no, this is really crucial, I keep it secret for a while. It's really hard to break through that unless you have, someone else really sort of putting the weight of the community behind it. And I see Mike with his hands up in a second. But the other component to this, right, is that often people are afraid to do this because they are afraid of what the code might look like or what people will look at and what they'll dig in. And that is the slow process of changing people's viewpoints, right? And that is social engineering, that is psychology, right? And no joke, right? It's developing that relationship with the group. And that can help, getting people over that barrier of just this anxiety that they don't want anybody to look at their code because nobody's looked at it in 2 years, and oh my God, right? And that's a real response people have. And so that's something you can do, which is help step.
So while Catherine's walking over there, I'll get out my soapbox on this particular topic and say, I don't believe there is any downside to making your code open source. I don't believe in the boogeyman of getting scooped because you made your source code open. I defy you to point to one solid example of someone actually getting scooped because they made their source code open source. Dare you. Do it. I don't know personally an example. Maybe one exists. But I do know plenty of examples of bugs being found. I do know plenty of examples of me releasing my code and then people contacting me and saying, hey, thank you so much for this. Would you like to be a collaborator on this? Right? I know lots of examples of that. And so I don't believe in the boogeyman of being scooped because of open source.
This is Mike Carew from Sandia. Thanks for a very nice talk.
Thanks.
This whole discussion the broader topic is called a business model. What's your business model for how you deal with your software? And open source is certainly a strong and viable one. But I think we have to be cognizant of other business models that involve closed source or actually blended open and closed, where you put the framework out there and the core physics and things that are well known, where you'd like innovation from the community, but then you may have some special physics that you shouldn't let out or that is your competitive advantage. And there's reasons to keep that in. And also I think we have to acknowledge that when you get in, the closer you get to a commercial software environment where people are building stuff that really matters on your software, and it's not just about discovery and writing papers,
right,
the more viability a closed source model has, because the business model has to include support. And support is the vast majority of any successful software product for something that lives a long time. And so I think the bigger issue is pick a business model that makes sense for you, that may include all open source, some open source, or all closed source. And that's a more holistic view from my point of view of software.
Yeah, no, I think that's completely a fair statement, and it should be stated clearly that my myopic view is very much from the pure science discovery aspect, and I'm so far away from commercialization, and I try to stay far away from physics that shouldn't be made open source. Well.
Hello. So there are so many open source code available, and you have shown that even really famous code could have bugs. So how do you find a code which can work for you? And if you find a code at the end of you submitted the paper, and eventually you found code 2 years later, what is to do at that time? Like, what is the best thing?
Yeah. So for finding a code that does what you needed to do, there are some resources. I mentioned ASCL.net. That's for astrophysics. I imagine there are similar repositories, databases in different domains. And then word of mouth is a big one. If you use a piece of code, it's open source, it was community code, you learn that there's a bug. The right thing to do is to probably issue an erratum. First thing you do is go and you test and you see, is this actually going to change my answer? And the first way to look at it is to look at the bug, read the code, and know what would have changed. The second thing is to actually rerun your calculation. Sometimes that's impossible, right? If you're burning 50 million core hours on one calculation, you can't, this line of code changed, right? That min should have been a max. Oh. The right thing to do is issue an errata and just point it out. And sometimes that's what you got to do. I think. I've had to do it.
There are sort of similarly, like for different communities, like molecular dynamics does do this, like have sort of pointers and discussions. But frankly, one of the other ways too is meetings, like conferences and workshops, right? You'll get exposed to it. You can often, you often have somebody who's there who's maybe using the code. You can talk to them. They might not be like one of the primary developers, but they're a user, and maybe possibly a user developer. It's another really good way to network about it, because frankly, having somebody also in the community that you can talk to who is using those codes, right? Coder codes. It's also really, it's incredibly valuable. That's all. I'll just leave it at that.